Hello, my dear student. Welcome to another edition of your mathematics lesson. Today, in continuation with your main topic, that is depreciation. What we are going to learn today is properties of depreciation. So let's begin. After completing the very lesson today, my dear student, will be able to find the derivative of a function that has more than one term. This is what I hope you'll be able to do after completing the very lesson today. So as usually in your favorite segment, Maths is fun. Today I'll take you through the use of mathematics to determine or to measure beauty of a face. That will be done after completing my lesson today, so don't go away. Now to begin the lesson, let us first take some of the properties of depreciation. So number one property, it says if you have the function y equals to c, where c is a constant number, just like you have y equals to 2, y equals to 3, y equals to 10. What will be the derivative there? So it says d by dx of that constant number c. The answer will now be 0. So this property simply tells us that the derivative of a constant number is 0. Let's move to the second property. Property number 2 says if you have the function y equals to cx raised to the power of n, where c and n are real numbers. So in this case, you can see c is just like a coefficient of x raised to the power of n. So in that case, what will happen to the derivative of y, the function y? It says d by dx of this term cx raised to the power of n is nothing but cn, that is c times n, then times x raised to the power of n minus 1. The power we learned in our previous lesson, after finding the derivative, the power will reduced by 1. But in that case, that power n will now multiply the constant number there, which serves as the coefficient of x raised to the power of n. So in this case, if you have, for example, y equals to 2x raised to the power of 3, that 3, the power will now multiply the 2, which serves as the coefficient. We shall see this in an example. So let's just move to property number 3. Property number 3 says if you have the function y equals to x raised to n plus x raised to m, where m and n are both real numbers. So what happened to the derivative? In this case, you can see that the function y has the 2 terms or more than the 2 terms. So the derivative of this will now be equals to, that is derivative of x raised to n plus x raised to m. This is nothing but the derivative of x raised to n separately, then add the derivative of x raised to m separately. Which means if you have a function that has more than one term, what you simply do according to this very property, you now find the derivative term by term. If it is addition, then you add the 2 terms, you add the derivatives. So let us just see one more property, number 4. It says if you have y equals to x raised to n minus x raised to m, where n and m are both real numbers. So there also, just like the property above, that is property number 3, you now find the derivative term by term, and you now subtract the 2 derivatives. These 4 properties will now be very, very useful in our finding derivative of some functions that involves more than one term. So let's just move and take examples. Example number 1, you are asked to find the derivative of y equals to x raised to 4 minus 5x raised to 3 plus 9. And this derivative is with respect to x. Solution to this very problem. What we now do first is to write down the derivative term by term. You can see that this function y has more than one term. I can see 1, 2, 3 terms there. So the derivative of this function will now be equals to the derivative of the very first term, that is x raised to the power of 4, minus, because it is minus here, then the derivative of the next term, that is d by dx of 5x raised to 3, plus the derivative of 9, which is the last term, there d by dx of 9. So I continue. So what I'm going to do next is to find the derivative of each term. Remember derivative, the power reduced by 1, and we now multiply that power by the coefficient of the unknown there. So in this case, I have 1 over here. So 4 times 1, it will be 4. Then that power 4 will reduced by 1. So derivative of this x raised to 4 is nothing but 4x raised to the power of 3. Then I continue. Derivative of 5x raised to 3. The 3 will now multiply 5 to get 15. And that power 3 will reduce by 1, so it becomes power 2. So then I'm going to have minus 15x raised to the power of 2. I continue. Then derivative of 9. 9 is just a constant number. We have just learned in this lesson. Property number 1, derivative of constant number is 0. So derivative of 9 as 9 is a constant number. That derivative is now going to be just 0. So I continue. So addition of 0 to this is simply give us 4x raised to 3 minus 15x squared. This is the derivative of this function y. So let us move and take another example. Example number 2, it says find the dy by dx if the function y is equals to 8x plus x raised to 3 minus x raised to the power of minus 1. Solution to this very problem. Derivative of this function, as it is having more than one term, will now be derivative term by term. So let me do that. So I have d by dx, dy by dx will now be equals to d by dx of the very first term, which is 8x, plus, because I have plus as what separate the first term and the second term, then the derivative of the next term, which is x raised to 3. So I have d by dx of x raised to 3, then minus d by dx of the last term, which is x raised to the power of minus 1. So I'll continue. So I'll now find the derivative of 8x. This x has power 1. So that one will now multiply 8 to get 8, and that one will now reduce by 1, so it will now change it to 0. So I'm going to have derivative of that x, 8x raised to the power of 0. Then the derivative of the next term. Next is x raised to 3. That power 3 will now multiply the one I have here, and that 3 will now reduce by 1, so it becomes 2. So I'm going to have simply 1x raised to the power of 2, 3x raised to the power of 2. This 3 will now multiply the one here, so you have 3x raised to the power of 2. Then I continue. Derivative of x raised to the power of minus 1. This power minus 1 will now multiply the one I have here, so I will get minus 1. And that minus 1 will reduce by 1. So minus 1 will now be minus 2. So I'm going to have minus x raised to the power of minus 2. So I'll continue. X raised to the power of 0 is nothing but 1. 1 times 8 will give me 8. So I'm going to have 8 here. 3x raised to the power of 2. Then this minus will now change it to plus, then x raised to the power of minus 2. This is the derivative of this function, that is dy by dx. With these two examples, I have come to the end of this very lesson, my dear students. I hope you find it resourceful, and let me just move to the last segment, Marcy's fun. Thank you for your attention. So let me take you through to use of mathematics to determine or to measure beauty of a face. I would just use these drawings of this very face as a typical example of a face. So it says, according to the Greeks mathematics, that is, beauty has to do with the proportion and the symmetry of the nose, the eye, the eyebrow, the lips, and so on. And these ratios, when compared to the golden ratio, that is 1.618. So if those ratios are close to 1.618, then that face is considered to be beautiful, almost beautiful, depending on how close it is. Let's just take typical examples of some of these ratios. So it says below are some of the standard graded beauty facial ratios and the symmetry. I'll take you through some of these proportions and some of this symmetry. Let me just use this typical example. So the very first one is the face ratio. The face ratio has to do with the ratio of the length of the face compared to the width of the face. if this is measured accurately and divided the two results, what we expect to have for beautiful face or for most perfect face is something close to 1.618. Similarly, another ratio is the distance from the end of the nostril to the beginning of the mouth compared to the heights of the two lips. So that is denoted by letter C, this distance, and this distance is denoted by letter B. So if you divided the height of the two lips divided by the distance from the end of the nose to the beginning of the mouth, this ratio also is expected to be very close to 1.618 for most perfect or for most beautiful face. Similarly, another ratio is the height of the two lips and the distance from the end of the lips to the end of this chin, denoted by letter A. So if this distance A is divided by this distance B, what you expect to have for most beautiful face is a value very close to 1.618. That is the golden ratio. Similarly, if you now take the width of the nose and the width of the mouth, this width of the nose is denoted by letter N, and the width of the mouth is denoted by letter M. So if you divide the width of the mouth by the width of the nose for most perfect face, this ratio will also be very close to 1.618. This is why they said the most beautiful face now obey this golden ratio as the facial ratios. There are other ratios, not only this that I just mentioned this very four. Let me just move to the symmetry of some of the face parts for very perfect face or for most beautiful face. The length beginning of the forehead to the starting of the eyebrow, from the start of the eyebrow to the end of the nose, and to the end of the nose to the end of the chin. These three distances supposed to be equal for most beautiful face. Similarly, another symmetry, look at it, the width of the eyes and the distance between the two eyes. Look at it. This is P, this is R, and the distance between the two eyes is denoted by letter Q. This also three distances supposed to be equal for most perfect or for most beautiful face. Similarly, another symmetry, the height of the nose, look at it, the length of the nose from this to this is denoted by letter K. And the height of your ears also for most beautiful face, this supposed to be equal. The two distances supposed to be equal for most beautiful face. And there are other many symmetries. These are just a few among them. So this is discovered by Greek mathematicians, and they said beauty can be measured, not just only using our subjective nature. So we'll see more of this in our next lesson. Thank you for your attention.